Hello, in this video we are going to see how to calculate the unknown load in curved beams. இந்த வீடியோவில் ஒரு curved beam ப்ராப்ளம்க்கு எப்படி ஒரு load value calculate பண்ணலாம் using the design data book BSG publication அப்படிங்கிறத பார்க்க போகிறோம். Let me start the problem now. A clamp is subjected to a maximum load of W as shown in figure. They have given the diagram which is kind of a C clamp. At the end of the C clamp, if the load is applied, the value is W. It is not given actually. And it has the cross section of T-shaped cross section the clamp has. Okay. And the dimension of T-shape is the vertical flange 19 cross 3. The horizontal flange 3 cross 22. Okay. These are the dimensions of the cross section. And then if the maximum tensile stress at the clamp is limited to 140 megapascal, find the value of W. So what they are saying is the diagram is given actually and the load value is the unknown one. They have said the maximum tensile stress acting on the cross section is 140 megapascal, then calculate the W value. அதாவது ஒரு C bracket மாதிரி உங்களுக்கு கொடுத்துருக்காங்க. இது ஒரு curved beam. அதோட எண்டில் W அப்படிங்கிற லோடு ஆக்ட் ஆகுது. அதோட வேல்யூ நமக்கு கொடுக்கல. And in the curved beam ஓட cross section என்ன அப்படின்னா T-shaped cross section. T-shaped cross sectionல பார்த்தீங்க அப்படின்னா அதோட vertical flange height 19, width என்ன அப்படின்னா 3. Horizontal flangeக்கு height 3, width என்ன பார்த்தீங்க அப்படின்னா 22. So these are the dimension of the T-shape for the cross section of C clamp. So இப்போ இந்த clampல ஆக்ட் ஆகிற total tensile stress என்ன கொடுத்துருக்காங்க அப்படின்னா 140 megapascal, அதாவது 140 Newton per mm square அப்படின்னு கொடுத்துருக்காங்க. So when the total stress is given, we need to calculate the load value. Yeah, fine. Now we can go to solve the problem. So actually, when the curved beam problem is given, we have to be more careful on the cross section. What type of cross section is given? So based on that only, we are going to solve the problem. From the design data book, page number 6.3. there will be so many cross section: I-shaped, squared, rectangle, circle, hollow square, T-shaped, H-shaped. So there will be different shape of cross section will be given. So we can match our given cross section to the particular page number. So 6.3 பேஜில் பார்த்தீங்க அப்படின்னா நிறைய cross section கொடுத்துருப்பாங்க. curved beam cross section ஸ்கொயராக இருக்கட்டும், சர்க்கிளாக இருக்கட்டும், ஹாலோ சர்க்கிளாக இருக்கட்டும், ஹாலோ ஸ்கொயராக இருக்கட்டும், ரெக்டாங்கிள், ஹாலோ ரெக்டாங்கிள், I-shaped, H-shaped, L-shaped, then and the mari shape. So there will be different shaped cross section will be there and the notation will be there. And the notation base பண்ணி என்ன பண்ணிக்கணும் அப்படின்னா நமக்கு தேவையான வேல்யூவை நம்ம கண்டுபிடிச்சுக்கணும். So from the diagram we can see that there is 3 axes actually. G is the centroidal axis, N is the neutral axis, O is the center of curved beam. So if you see the diagram, the entire beam is kind of curved. Okay. So here the O is the center of curve actually. The curved beam will be like a bended beam and the O is the center of the curve. And G is the centroidal axis. Centroid means we know that if there is any shape, we can mark the centroid of the shape. The axis which is passing through the centroid of the cross section is centroidal axis. And there will be a neutral axis based on the cross section where the bending stress is 0. So there will be a centroidal axis and the neutral axis. For a curved beam, there will be deviation from centroidal axis and neutral axis. Normal beam curve இல்லாம ஒரு straight beam பார்த்தீங்க அப்படின்னா centroidal axisம் neutral axisம் ஒரே லைனா coincide ஆயிருக்கும். So in a normal straight beam, the centroidal axis and the neutral axis will be coinciding. If it is a curved beam, the neutral axis will be deviated from the centroidal axis. So curved beamல பார்த்தீங்க அப்படின்னா இந்த சென்ட்ராய்டல் ஆக்சிஸ்ல இருந்து நியூட்ரல் ஆக்சிஸ் என்ன இருக்கும் அப்படின்னா கொஞ்சம் டீவியேட் ஆகியிருக்கும். அந்த டீவியேட் ஆன டிஸ்டன்ஸ் தான் என்ன அப்படின்னா எசென்ட்ரிசிட்டி E. ஓகே. இப்போ நம்ம என்ன பண்ணலாம் அப்படின்னா we can see different notation from the diagram. So first of all, RI. So RI is the distance between center of curvature to the inner fiber of cross section. So up to inner fiber, that is RI. Up to outer fiber, the distance is R0. So RI is the distance between center of the curvature and the inner fiber. RO is distance between center of curvature O to the outer fiber. that is RO, and Rn is distance between center of curvature to the neutral axis, and R mean radius, which is nothing but the distance between center of curvature to the centroidal axis, centroidal point, and E is the distance between centroid axis and neutral axis, and HI is distance between inner fiber to neutral axis, and H not HO is distance between neutral axis and the outer fiber. So these are the different notation we are going to use in the calculation. This is the different notation we are going to use in the calculation. Ri, R naught, Rn, capital R, that is mean radius, and eccentricity E, Hi, Ho. These are the different notation, and also the size of the flange. So what is size of flange is the vertical flange height, that is Bi 19 mm, then Ti 3 mm, T 3 mm, H 25 mm. H is nothing but total horizontal distance of the cross section. So these Bi, Ti, T, H, everything will be mentioned in the diagram of page number 6.3. So if you are watching the video, get you a decent data book of PhD publication, go to page number 6.3 and refer the diagram given in the page number. Okay, in the particular page number, the T cross section will be there. Refer all the notation. So among the notation, we can simply identify that few of the values. So Ri, which is nothing but the distance between center of curvature to inner fiber, that is 25 mm, which is given in the diagram itself. In the diagram, they have given like that. In the diagram, center to inner fiber, the distance is 25 they have given. So we can simply say, and the distance of Ri is 25, and they have given the width of the cross section. Width of the cross section is 25. So we can see that center to outer fiber 25 and plus or 25, 50. So Ri and R naught, we can simply say Ri 25 mm, R naught 20, already 25 is there, and then 3 mm, then 22 mm. So 22 plus 3 plus 25 is equal to 50 mm, totally 50 mm. So similarly, we need to calculate Rn value, capital R value, Hi value, H naught value, E value. So once we calculate capital R and Rn, we can calculate the remaining dimensions. Okay, in the same page 6.3 itself, there will be the formula for capital R and small rn. And for small rn, there is a formula which including all the notations BIT, TIT, H, total width of the cross section, then BIT. So all the values, you know it already from the diagram, and by matching your diagram with the page number 6.3, you can get all the dimension by simply substituting all the dimension in the particular formula given in page number 6.3. You can calculate Rn value. ஸோ அகைன் சொல்கிறேன், பேஜ் நம்பர் 6.3 பார்த்தீங்க அப்படின்னா உங்களுக்கு கொடுத்த கிராஸ் செக்ஷன் அங்கே மென்ஷன் பண்ணியிருப்பாங்க. அதுக்கு பக்கத்துலேயே ஸ்மால் ஆர்என்னுக்கான ஃபார்முலா. ஸ்மால் ஆர்என்கிறது டிஸ்டன்ஸ் பிட்வீன் சென்டர் ஆஃப் கர்வேச்சர் டு தி நியூட்ரல் ஆக்சிஸ், அதுக்கான ஃபார்முலா இருக்கும். அந்த ஃபார்முலாவில் உள்ள அத்தனை வேல்யூமே உங்களுக்கு டயக்ராமில் மேட்ச் ஆகிருக்கும். அந்த வேல்யூ எல்லாம் சப்ஸ்டியூட் பண்ணிங்க அப்படின்னா you can calculate Rn value. Similarly, the mean radius, the distance between center of curvature to the centroidal axis, capital R. In the formula also, there will be values which we can get from the diagram, and by simply substituting all the value, like Ri is equal to 25, H is equal to 25, T is equal to 3, flange thickness, then Bi is equal to flange height 19 mm. Like that, if we substitute all the value from the diagram, we can get the capital R value from simple calculation. And here I can get Rn is equal to 31.64 mm and R capital R is equal to 33.2 mm. So we can see the diagram here. We know Ri value, we know R naught value. Similarly, Bi, T, Ti, then total value H 25. So we know all these value from the diagram. By substituting all the value, we can calculate capital R and small rn, by using the formula which is taken from page number 6.3 of Design Data Book PhD publication. Okay. Okay, and now we can find other dimension like h naught, E, Hi from the Rn value and capital R value. Okay, look at here, the total distance O to N, center of curvature to neutral axis is Rn. Okay, so if you know Rn and Ri, Rn minus Ri is equal to Hi. So can you understand the diagram? Rn value we have calculated, Ri is 25 mm we know, Rn minus Ri we can get Hi value. And similarly, total distance to outer fiber is R naught and we know Rn value. So R naught value minus Rn value we can get H naught value. We can get H naught. So Hi is equal to Rn minus Ri, H naught is equal to R naught minus Rn. So like that, by calculating Rn value and if we know Ri and R naught value, we can calculate Hi and H naught value from the diagram itself. So clear. And then eccentricity value. And we know that eccentricity is nothing but distance between the centroidal axis and neutral axis. So the total distance from the curvature is R to centroid axis and the total distance from center of curvature to neutral axis, that is Rn. So capital R minus Rn is equal to E. Capital R minus Rn is equal to E. So simply calculating Rn value and R value, we can calculate the other dimensions Hi, H naught and E. Okay, why we are calculating all these dimensions mean we need to calculate the load value which is not given in the stress formula, and we should know what are the stresses involved in the particular curved beam, and by calculating the stress values by substituting the load value we can find the unknown. Okay, let me see what are the different stresses acting on the curved beam. Okay, so in the page number 6.3 கொடுத்திருக்க diagram and formula மூலமா நமக்கு தேவையான Rn value, capital R value இது எல்லாமே ஃபைண்ட் பண்ணிடலாம். இதான் ஏன் ஃபைண்ட் பண்ணுறோம் அப்படின்னா நமக்கு லோட் வேல்யூ தான் என்ன பண்ணணும் அப்படின்னா கால்குலேட் பண்ணணும். லோட் வேல்யூ கால்குலேட் பண்ணணும் அப்படின்னா we need stress value. ஸோ ஸ்ட்ரெஸ் வேல்யூக்கு ஸ்ட்ரெஸ்னால் என்ன, லோடு பை ஏரியா அப்படி தானே. லோடு பை ஏரியாங்கிறது ஸ்ட்ரெஸ்ஸுக்கான சிம்பிள் ஃபார்முலா. ஏரியாவில் என்ன இருக்கும், டைமென்ஷன் இருக்கும். ஸோ we should know all the dimension and we should know the stress value which is given the problem, then we can calculate the load value. Okay, so we can analyze the diagram to calculate or to identify what are the different stresses will be induced in the particular curved beam. Okay, so let me see the first diagram. So in the first diagram we can see there are three different axes. G is centroidal axis, N is neutral axis and O is the axis through the center of curvature. Okay, and fourth one is the load acting point. So the load is W which is acting at the end of the clamp. Okay, so we can see that from the centroidal axis the load is deviated from. Okay, அதாவது சென்ட்ராய்டல் ஆக்சிஸ்லேயே ஒரு லோடு ஆக்ட் ஆச்சு அப்படின்னா டைரக்ட் ஸ்ட்ரெஸ் மட்டும்தான் இருக்கும். டென்சைல்னா டென்சைல் இருக்கும், கம்ப்ரெசிவ்னா கம்ப்ரெசிவ் இருக்கும். இஃப் எ லோட் ஆக்டிங் ஆன் தி ஆக்சிஸ் ஆஃப் த பீம், சென்ட்ராய்டல் ஆக்சிஸ் ஆஃப் த பீம், தென் there will be only tensile and compressive stress. But when the load acting point is parallel to the centroidal axis, there will be another bending load will be there. So இப்போ என்ன ஆக்ட் ஆகுது அப்படின்னா the load will be acting eccentric from the centroidal load. அதாவது ஒரு centroidal axisலேருந்து eccentric-ஆ என்ன ஆகுது, load act ஆகுது. So we have to resolve the forces. We have to resolve the eccentrical loading condition. Okay, so how we can resolve this? I simply add one force and subtract one force at centroidal axis. ஸோ சென்ட்ராய்டல் ஆக்சிஸில் நான் என்ன பண்ணுறேன் அப்படின்னா அப்வர்ட் டைரெக்ஷனில் ஒரு ஃபோர்ஸ் ஆக்ட் பண்ணுறேன், அதே மாதிரி டவுன்வர்ட் டைரெக்ஷனில் ஒரு ஃபோர்ஸ் ஆக்ட் பண்ணுறேன். இதுவும் வேல்யூ W தான், இதுவும் வேல்யூ W தான். ஸோ இது டவுன்வர்ட் நெகட்டிவ்னு வச்சுட்டிங்க அப்படின்னா டவுன்வர்ட் நெகட்டிவ், அப்வர்ட் பாசிட்டிவ். ஸோ சம்மேஷன் பண்ணிங்க அப்படின்னா நெகட்டிவ் நெகட்டிவ் கேன்சல் ஆகி உங்களுக்கு ஆன்சர் வரும் அப்படின்னா -W தான் வரும். ஸோ ஆன்சர் சம்மேஷன் ஆஃப் ஃபோர்ஸ், ரிசல்டன்ட் ஃபோர்ஸில் எந்த சேஞ்சும் இருக்க போகிறதில்ல. ஸோ நான் என்ன பண்ணுறேன், இமேஜினரியாக ஐ ஆம் ஆடிங் upward force and downward force through the centroidal axis. Okay, add பண்ணியாச்சு. After adding that we can see like these two forces, one is moving upward direction, the value is W. Another one is moving downward direction, value is W. Actually these two forces are parallel and opposite to each other and having same value, which will form the couple. அதாவது ரெண்டு ஃபோர்ஸ் ஒன்றுக்கு ஒன்று பேரலாக ஆப்போசிட் டைரக்ஷனில் இருந்துச்சு அப்படின்னா ஒரு எலமெண்ட்டில் ஆக்ட் ஆகுது ஒரு பாடியில் ஆக்ட் ஆகுது அப்படின்னா that will form a couple. ஸோ கப்புள் பார்த்தீங்க அப்படின்னா இது டவுன்வேர்டாக இது அப்வேர்டாக. ஸோ கப்புள் பார்த்தீங்க அப்படின்னா உங்களுக்கு கிளாக் வைஸ் டைரக்ஷனில் என்ன ஆகும் ஒரு கப்புள் ஃபார்ம் ஆகும். ஸோ டியூ டு கப்புள் there will be a bending load. There will be a bending load. So bending stress we need to calculate. Okay, fine. And இப்போ among the three forces, one force is there and I have added two forces. Among the three forces, two forces will form a couple. இப்போ remaining one force எங்கே இருக்குன்னு பாரு. The remaining one force is acting along the centroidal axis downward direction. Downward direction is kind of pulling force. So there will be a direct tensile. There will be a direct tensile. So among the three forces, two forces form a couple and the one remaining force is kind of a tensile force. So we have to calculate the direct tensile stress and a bending stress Okay, fine. Now we can calculate the stresses. There are two stresses involved. We have seen that one is the direct stress and another one is the bending stress. Okay, and the direct stress sigma d is equal to, direct stress means load by area, that's it. Direct stress means load by area. Load is the unknown load. Area is the area of T shape. And we can see the T shape actually. I'll draw here. This is the T shape. And we can see the T shape is kind of two rectangle. 3 into 22, 3 into 19. There is two rectangle. By adding the area of two rectangles, we can get the area of the T shape. So area is 3 into 22 and 3 into 19. So area is calculated and the load is unknown W. Let me remain W. Okay. So sigma D is equal to 0.008 W. So load will be is in terms of W. Okay. Okay. That is the sigma D direct stress value. And another one is bending stress. And there will be two bending stresses by seeing at inner fiber and outer fiber. So inner fiber there will be a tensile stress and outer fiber there will be a compressive stress. We can see like that here in the curved beam. Let me explain the diagram itself. Okay. So here actually due to bending what will happen is the bracket will be kind of bending like that. Okay. If the bending failure occurs, the entire clamp will be bending like this. அதாவது bending நடந்துச்சு அப்படின்னா மொத்த clamp என்ன ஆகும் அப்படின்னா இந்த மாதிரி bend ஆகும். So at the inner fiber, இதான் inner fiber, இது outer fiber. At the inner fiber there will be material elongation, there will be a tensile. At the outer fiber there will be a compression, there will be a material contraction. So comparatively when there is a curved beam at inner fiber there will be a tensile force having more stress value. So inner fiber will be at the inner fiber there will be more stress comparatively the outer fiber. So okay, so whenever you are going to calculate the bending stress, calculate the bending stress at the inner fiber. Okay, because at the inner fiber the stress value is maximum comparatively outer fiber, because inner fiber is affected by the elongation of material which will be resulting in higher stresses. Okay, there is a formula in page number 6.2. There is a formula in page number 6.2 for inner fiber and outer fiber. Inner fiber sigma bi, outer fiber sigma bo. There will be two formula. If you have any doubt, you can calculate both value. Obviously sigma bi will be the maximum. You have to choose the maximum value among the two. So you can calculate the sigma bi instead of calculating both values. Okay. Okay, sigma bi formula which is m into hi divided by aeri. M is the bending moment, hi is the dimension from the diagram, ri distance between inner fiber and center of curvature, a is the area, small e is the eccentricity. So we know all the value here except the load value. Okay, what is bending moment actually here? How can I calculate this? Here, this is your diagram. So how can we calculate the bending moment? Bending moment is nothing but the moment is equal to load into perpendicular distance. The distance from the centroidal axis to the load acting point, that is x actually. Okay, from the centroidal axis to the load acting point. Okay, So here the load is acting. So up to center of curvature the distance is 50 they have given. We can see here up to center of curvature the load acting point is 50 mm away, and from center of curvature to centroid that is capital R. So capital R plus 50 is equal to x. So from the diagram itself we can see here, again I am explain in the particular diagram. Actually what is the distance for bending moment is the distance between centroidal axis to the load acting point, and the distance from center of curvature to load is given is already, what is the value is 50, and center of curvature to centroidal axis is capital R. So if it is x is equal to capital R plus 50. Okay, that's what we are going to calculate. So here bending moment M is equal to W into x, and W into x is equal to R plus 50. R is equal to 33.2 plus 50, 83.2. So by substituting all the value in the bending moment formula, HI is equal to 6.64 mm, area, that area of the T shape, E is equal to 1.56 mm, Ri is equal to 25 mm, and X is equal to 83.2, we can get sigma BI is equal to 0.116 W. In terms of W we can calculate. And after that the total tensile stress is given in the problem. Total tensile stress 140 megapascal, which is given in the problem, which is nothing but Newton per mm square. Total tensile at the inner fiber sigma D tensile plus sigma B tensile. Why it is tensile is at the inner fiber there will be elongation due to bending, at outer fiber there will be compression due to bending. So we are seeing at the inner fiber only. In inner fiber due to direct load there is a tensile, due to bending load there is a tensile. So plus sigma D plus sigma BI. By adding sigma D and sigma BI we can equate with the total stress value 140. Sigma D is equal to 0.008 W. Sigma BI is equal to 0.116 W, that is equal to 140 Newton per mm square. 140 Newton per mm square. And here W is the only unknown value. We can calculate the W, which we can get is 1138 Newton. அதாவது இன்னர் ஃபைபரில் பார்த்தோம் அப்படின்னா டைரக்ட் லோடால் ஒரு டென்சைல் நடக்கும், பெண்டிங்கால் ஒரு டென்சைல் நடக்கும். அவுட்டர் ஃபைபர் பார்த்தீங்க அப்படின்னா டைரக்டால் ஒரு டென்சைலும் பெண்டிங்கால் கம்ப்ரெஷனும் நடக்கும். ஸோ டென்சைல் ப்ளஸ் டென்சைல் அதுதான் வந்து மேக்ஸிமம் வேல்யூ கிடைக்கும். ஸோ வி ஹவ் டு கோ ஃபார் இன்னர் ஃபைபர். இன்னர் ஃபைபரில் total stress value 140 Newton per mm square, that is equal to sigma D sigma BI. So that is 0.008 W plus 0.116 W, which we can equate with 140. Then the W will be the unknown. The W value is 1138 Newton. Okay, this is how we can calculate the load value for the curved beam problem by using the eccentricity loading condition. Okay, thank you.